Okay, measures of relative standing. A statistical measure that describes the position of a particular data value relative to the other values of the data set is a measure of relative standard. In a distribution of test scores out of 100, the position of a score of 99 would be far right of average. However, in a distribution, if the distribution were describing IQ scores, where the average IQ score is approximately 100, a data value of 99 would just be considered average. A data value can have different interpretations based on its standing within a distribution. So a 99 could be great or a 99 could be average depending on where its position is, its standing within a distribution. So that's where we come up with the concept of z-scores. A z-score of a data value indicates the number of standard deviations that the data value deviates from the mean. Each data value of a distribution has its own z-score that indicates how far from the mean the data value lies. For a data distribution with a mean of 25 and a sample standard deviation of 3, the data value 28 has a z-score of 1 because it is one standard deviation away from the mean. Data value of 31 has a z-score of 2 because it is 2 standard deviations away from the mean. A data value of 22 has a z-score of -1 because it's 1 standard deviation below the mean. So you can have z-scores that are positive and z-scores that are negative. Okay, so here's our, we did this example just before. Here are our raw values, our raw scores, 16, 19, 22, 25, 28, 31, and 34. 25 is the mean. A data value of 28 would have a z-score of 1 because it's just 1 standard deviation above the mean. 31 would have a z-score of 2. 34 would have a z-score of 3. 22 would have a z-score of -1. 19 would have a z-score of -2. And 16 would have a z-score of -3. And 25 would have a z-score of 0. So here are our z-scores. They range from -3 to +3. Any data value that has a z-score that's greater than 3 or less than -3 would be considered an outlier because its standard deviation is more than 3, or rather its value is more than 3 standard deviations above or below the mean. Okay, its value is more than 3 standard deviations above. So if we take a look at data values that fall between 25 and 28, for example 26, we have to come up with a way that we can take a z-score and turn it into a decimal, because z-scores aren't only whole numbers, they can have decimal parts to them. So we're going to have to figure out a way to convert a raw score like 26 into a z-score. Okay, so the formula for a z-score is you take the data value that's in your distribution, you subtract the mean of the distribution, and you divide by the standard deviation. And we have two different, we can look at this for a sample, we could look at it for a population. For a sample, x minus x bar over s. For a population, x minus mu over sigma, because the means are denoted by different letters when you're dealing with a sample versus a population, and the standard deviations are different letters when you're dealing with a sample versus a population. We still use the letter z. It's still denoted by a z-score no matter what, as far as it will be a z-score for a sample, it will be a z-score for a population. Okay, so we are going to take a look at how z-scores can be calculated. Debbie earned a grade of 87 on her history exam and a grade of 39 on her English exam. 87 and 39 are raw scores. Okay. She would like to determine on which exam she did better relative to the students in each class. How can this be accomplished using the information from table 3.16? Okay, so let's take a look at the information. In the history class, the mean for the entire class was 75. The standard deviation was found to be 6, and Debbie's grade was an 87. So 87 is above the mean, and we have to figure out what her z-score is. In English, the class mean was 27, the standard deviation was 4, and Debbie got a 39. So we're going to calculate her z-score in the English class as well. So there'll be two z-scores, a z-score for the score of 87 and a z-score for the score of 39. So the two raw scores will have associated z-scores. If we can find how many standard deviations each grade lies from the mean of the class, we can determine which grade is better relative to the rest of the class. Okay, so let's assume the mean is in the center. Lower z-scores are closer to the mean, higher z-scores are further away from the mean. If a student scores close to the mean, they didn't score as well as students who scored higher away from the mean. Okay, so if the mean is 75, a low z-score could be a score of 79, where a high z-score could be a score of 85. Okay, so lower z-scores aren't as for this example anyway, lower z-scores are closer to the mean and therefore not as outstanding as higher z-scores. Okay, so better grades will be far above the mean. The number of standard deviations will be greater than that of lower grade scores. Now, if you take a look at what happens on the other side, these students scored less than the mean. Okay, so any student that scored less than the mean would have a z-score that ends up being negative. Now, if you're interested in passing, you probably don't want too negative a z-score. So a -3 would not be good. You don't want to be far away from the mean in that case. If you get a -0.5, you're not so far away from the mean, and that would probably be better for your average. Okay. Okay, so looking at the data again, the definition of a z-score is the number of standard deviations a score lies away from the mean. So for the history grade, we can use the formula for a z-score, x minus mu over sigma. So the data value is x. The data value is Debbie's grade. Mu is the mean of the class. Sigma is the standard deviation. So plugging that into the formula, we have 87 minus 675 over 6, and that gives us a z-score of 2, exactly 2. For the English grade, we can do the same calculation where the data value is 39, the mean is 27, and the standard deviation is 4. 39 minus 27 over 4, and the z-score comes out to be 3. I just want to demonstrate if you choose to do this on your calculator, because we may not always get whole number z-scores, so you'll need to do this on your calculator sometimes. Okay, if you do 87 minus 75, because it's in the numerator, you must put it in parentheses. So parentheses 87 minus 75, close parentheses, divided by 6 is 2. Same thing for the other one, 39 minus 27 divided by 4 is 3. Okay, a z-score of 3 is pretty outstanding because it's 3 standard deviations above the mean. A z-score of 2 is good too, but not as good as a z-score of 3. So the class in which she did better relative to everybody else would be the English class, because that z-score is higher, and a z-score is a measure of standing in the class. So looking at a diagram here, in the history class she scored an 87, which is 2 standard deviations from the mean. Okay, 12 points away from the mean was 2 standard deviations away from the mean. In the English class, though, there's a whole 3 standard deviations away from the mean that she scored, which is more outstanding. So Debbie did better on the English exam because a z-score of 3 for the English exam is greater than a z-score of 2 for the history exam. Z-scores measure relative standing. So you want to be able to recognize that z-score is a measure of how a score lies in its distribution.